All right, we're continuing with example 11.4. I didn't quite get this example problem finished in the last video, so we're going to wrap this up and then move on. So we just found the velocity at an arbitrary point in the motion of our simple harmonic oscillator. And the next part of this question wants to know the maximum acceleration. Okay, so how can we find maximum acceleration here? Well, we know Newton's second law of motion states that F equals ma, and so if we want to know A, we can say that A is equal to the force divided by the mass. So to find the maximum acceleration, we need to know the maximum force. And the force in a spring is equal to kx. So the maximum x is the amplitude a, so the maximum force would be equal to the spring constant times the amplitude. Okay, so acceleration is going to equal Ka, that's our maximum force, divided by the mass. Our spring constant was 19.6. That's what we calculated at the very beginning. The amplitude is 0.100 meters. That's how far we pulled the block to the side when we let it go. And the mass of the block is 0.300. So 19.6 times 0.1 divided by 0.3 equals 6.53 meters per second squared is the maximum acceleration of the block. Okay, still continuing with the same oscillator with the same amplitude and mass and maximum velocity, we want to know the total energy and what is the kinetic and potential energies at half amplitude. Okay, so the easiest point to find the total amount of energy is either when the block is at x equals 0, which is the point where the spring is completely relaxed, or when the spring is completely stretched out to its amplitude. That's the one we're going to go with, where the spring is completely stretched out. So that energy is going to be completely 100% stored up potential energy in the spring, which is equal to 1/2 kx squared. But when it's completely stretched out, our x is going to be equal to the amplitude a. So we can say 1/2 ka squared is the total amount of energy in the system. So that's equal to 1/2 times, again, our spring constant was 19.6, and amplitude is 0.100. Don't forget to square that. And so 1/2 Ka squared is equal to 9.80 times 10 to the negative second. And our units here for energy are joules. Okay, and then if we move on to the next part of the question, the next part of the question was asking at half amplitude, what is the potential and kinetic energy? So let's first look at the potential energy. The potential energy in the spring is equal to 1/2 kx squared. So that's equal to 1/2 times our k of 19.6. And this time, instead of being stretched out to our full 0.100 amplitude, we're going to see what is the potential energy at half the amplitude. Half the amplitude is 0.050 squared. So 1/2 kx squared at half amplitude should equal 2.45 times 10 to the negative second joules. Okay, and then the kinetic energy. How much kinetic energy does it have at half amplitude? Well, we could directly solve for kinetic energy, but we would have to find the maximum velocity and then the velocity at half amplitude, and it would just be more steps. It would be a little bit more complicated. What is a little bit simpler is to just find the total amount of energy, subtract from it the potential energy, which we just found here, and what's left is equal to our kinetic energy. And so we already found the total energy in the system. If I jump back here, a little too far, total energy of the system is equivalent to the potential energy when the spring was stretched out to its maximum. So that right there is the total amount of energy in our system, 9.80 times 10 to the negative second. So if I start with that as my total, 9.80 times 10 to the negative second, and I subtract from it the potential energy, 2.45 times 10 to the negative second, what I'm left with is 2.45 times 10 to the negative second. No, I'm sorry. That's not right. Just looking at the wrong number in my notes here. It's equal to 7.35 times 10 to the negative second joules. Okay, so that's the simpler way of finding the kinetic energy. Just take the total amount of energy minus potential. Whatever is left over must therefore be kinetic. Okay, so here's a slight variation on our spring-based simple harmonic oscillator. Let's say we had a flat frictionless table and we had a string attached to a ball or some mass here, and this mass went around in a circle. Well, when we look at it from above, it would look like it's traveling in a circle. But if we got down right at table height and looked at it from the side, we wouldn't be able to see the motion in this direction, in the y-axis. All we would be able to see is the x-axis. And so it would just look like this ball is going back and forth, which is essentially the same as our simple harmonic oscillator that's based on a spring. And so in this particular case, in this variation here, we can calculate the velocity of the mass by plus or minus the maximum velocity, which is the tangential velocity of the mass, multiplied by the square root of 1 minus x squared over a squared, where x, again, is going to be our distance away from the center point, and a is the maximum distance away from the center point, which would basically be the radius of the string up here. So again, this is essentially, it behaves the exact same way as the spring-based oscillator. It's just a slight variation. We have to think back to our circular motion formulas and reuse some of these things. So the period, t's period, how long does it take for the mass to go all the way around in the circle, or as we look at it from the side, to go from side back again, one full cycle. That period is equal to 2 pi times the square root of m over k. And the frequency is just the inverse of the period, and that's 1 over 2 pi times square root of k over m. Okay, so if we continue to look at the variation of our simple harmonic oscillator based on circular motion rather than spring going back from side to side, we can locate the position of the spinning mass at any point in time using this equation. It's the amplitude times cosine of omega t. Remember, this is omega. This is also omega. And we can write that in a couple different ways as well, just substituting some things into the equation to get some varying forms here. So a times cosine of 2 pi ft, or a times cosine of 2 pi t divided by big T. So little t is time, big T is the period. So if we look at the idea of a simple harmonic oscillator a little bit more, let's say we have one. I know gravity comes into play here when we have it oriented vertically, but let's just say for an instant that it doesn't, that this box is just going to bob up and down and continue to do so at the same period. If this were attached to some sort of a pen that could draw on a piece of paper that's scrolling by here, what we would see is that as this box bobs up and down in an oscillating motion, and the paper continues to roll at a constant speed, the pattern drawn onto the paper ends up being a sine wave up and down and up and down. So basically, sine waves are an excellent way to graph the motion of an oscillating object with respect to time. So time is on the horizontal axis, position, or x, is on the vertical axis, and we can see that if we start at rest, we go all the way up to the amplitude, and then back to a position of rest, down to the negative amplitude, and then back up. That one full sine wave, starting at 0 and going up and down and back again to 0, that right there is one cycle. Okay. And here we just have the formulas for velocity at any given point in time based on the maximum velocity, and then the acceleration as well of the object at any given point in time if we know it's a maximum acceleration. And these functions are graphed here as well, and we see they are also sine or cosine waves. So we've got displacement, velocity, and acceleration, all showing similar graph shapes when graphed with respect to time. So the next type of oscillator that we're going to talk about is a pendulum. So a pendulum, made famous by Edgar Allan Poe in the story The Pit and the Pendulum, is basically just a mass suspended from a string or cord. And if we give this some initial horizontal motion, it's going to swing out to one side and reach its maximum amplitude, and then it's going to swing back in the other way and reach a negative amplitude there, and we'll continue to swing back and forth, back and forth. So a pendulum is close to being a simple harmonic oscillator, but not exactly. So the reason I say that is because the restoring force, the force that's going to bring the mass here back to its original position, is comes from gravity, which has a component in this direction that's going to bring it back to the original position. But it also has, obviously, a vertical component, and eventually over time, if you allow a pendulum to swing back and forth, it doesn't continue to go on and on forever. Eventually that pendulum will come to rest because of gravity's wanting to pull it straight down. So So the further away, the more you pull this back, the bigger the amplitude is.